Let's take a look at our last lesson for Chapter 4. So the name of this section is Evaluating the Linear Model. So we talked in the last lesson about looking at the equation of a linear model, the line that describes the regression equation. And so now we're going to look at how can we evaluate that model and tell how good it is. So a few things to note. Do not use linear models to describe nonlinear associations. So remember, everything we're going to talk about is going to be a linear model, but always work with linear models and don't use any kind of a line to describe something that's not linear. If you look at the graph and see that it's shaped like a curve or something like that, we need a different model to describe it. Correlation is not causation. So I didn't leave you much room here, so you're going to have to write small. So correlation is not causation. And what do we mean by that? Causation. I apologize, there's not a lot of room to write. We talked about that a little bit back in Chapter 1, that there were certain things that we had to have in an experiment to be true in order to show a cause and effect relationship. That is not the case when you're just looking at a linear model. Just because there's a strong association between two variables, that doesn't mean that one causes the other. You've probably heard that expression before. Correlation does not mean causation, and this is a good example of that. When you're looking at a linear model, you may have a really strong association. It's tempting to say that the independent variable caused a change in the dependent variable, but that is not the case. So keep that in mind. Beware of outliers. So beware of outliers. So outliers can have a big impact on R. So always make sure you look at the scatter plot and see if there are any outliers that you need to consider. And then the last one here is do not extrapolate. It's a big word, extrapolate. So do not extrapolate. That means you're making predictions beyond the range of data. We can only talk about what we know for the data in terms of whatever range we're working with. So if our data, the X values range from 10 to 50, we can only make predictions within the 10 to 50 range. Beyond that, we're doing what's called extrapolating, and we can't do that. So our model is only good for the range of data that we were working with. All right, so let's look at an example. Continuing with this example we had from a previous section, we found a strong linear relationship between the weight and height for a group of women. So our weight based on our height was given by this model. And the question, if you'll remember, and it's going back a couple sections, but we were looking at, I think it was 8 women, and their ranges for their heights were from 61 to 68 inches in our data. So the question says, what does this equation predict for a woman who is 36 inches tall? Do you see a problem with that? So 36 inches probably isn't a realistic height for an adult woman, but that aside, the issue is that is outside of the range of data we were working with. So we're not going to even bother to calculate this. So don't calculate, because this would be doing what? Since 36 is outside the range of data, this would be extrapolating. So that's what we want to avoid. So this would be extrapolating. So I'm not even going to compute it because it wouldn't make sense, because it's not in the range of data that we were starting with. The range of data for the women was 61 to 68 inches, as we just said. So therefore, it is not appropriate to use the regression equation to predict the weight for a 36-inch tall woman, since 36 is outside of the range of data. So there's a little more formal explanation. All right, so one tool we can use to evaluate how good our model is to use what's called the coefficient of determination. So the coefficient of determination is just computed. It's very easy to compute by hand. It's R squared. Remember, R was the correlation coefficient. So when we square it, we get the coefficient of determination. We usually convert it to a percentage, so it's always some percentage between 0 and 100%. And what does it mean? It measures how much variation, let me write that again. How much variation in the response variable, or the y variable, is explained by the explanatory variable or the x variable. So it kind of gives us an idea of how good our model is. The larger the r-squared value, the smaller variation or scatter there is, which means it's a really strong correlation. So you want to shoot for a higher coefficient of determination when you're setting up a study or something like that. That would mean that you've got a stronger association. And that means that it gives you an idea of how good your model is. The higher the coefficient of determination, if you're looking at different models, the better that model fits the data. And so suppose the data on a car's age is predicted by monetary value and produces a correlation coefficient of negative 0.778. I think we had this from a previous example, but the correlation coefficient was negative 0.778. So compute and interpret the coefficient of determination. And so to compute it, it's very simple. I'm going to just square the r value, and when you square a negative number, of course, it becomes a positive number. So it doesn't matter whether r is negative or positive. I get 0.605, and we're going to change that to a percentage by moving the decimal over 2 spots. So I get 60.5%. So what does that mean? That means about 60.5% or 61% if you want of the variation in the car's value is explained by the independent variable, which was the car's age. Oops, sorry about that, by the car's age. All right. If you had two models and you're trying to see which one better fits the data, you want to go with the one with the higher coefficient of determination. All right, so quick review for this chapter. The scatter plot below shows what type of relationship between the number of runs scored and the number of hits for a group of baseball players. So you can see what's happening as the runs scored increases, the number of hits tends to also increase. So we could say that this is and I don't have the R value, so it's hard to say exactly. It looks like it's pretty strong. If you're not comfortable with that, you could say a moderate, but it is positive. That's the most important thing, and it is linear. So a strong, positive, linear association or correlation is how we would describe that. So the three things we had mentioned: the shape, it's linear. The trend, it's positive, and the strength, we can say strong or maybe moderate if we're not comfortable because we don't have the R value with us. All right, number 2, there's a negative association between the percentage of smoke-free homes and the percentage of high school students who smoke. So what does this mean? Let's write a statement on this. So the independent variable, so let's read that again. The negative association between the percentage of smoke-free homes, the one they list first should be the independent variable, and the percentage of high school students smoke. So the second one should be your dependent variable. So let's describe it in terms of the independent first. We'll say as the percentage of smoke-free homes increases. So we always describe it in terms of an increasing independent variable. The percentage of, I'm just going to abbreviate and say HS, high school smokers. Since it's a negative association, what does that mean? Does it tend to go up or does it tend to go down? It tends to go down because the negative association tends to decrease. All right. For a certain group of cars, there's a strong association between the city and the highway mileage that can be described by this equation. So the city MPG versus the highway MPG. The city MPG predicting the highway MPG. MPG is miles per gallon. So city is the independent. So the number in front of that is our slope. Remember, we can put that over 1 if that helps us think about it. So we could say for every additional city, so every additional 1 is really what I'm saying. Every additional 1 city miles per gallon that a car gets. Let's see, the car will get, and I'm going to say will get about or approximately, because there's always a little uncertainty there, about 0.87 highway miles per gallon. So you describe it in terms of the 1 unit for the denominator, that's your independent variable, and then it's going to increase by about 0.87 highway miles per gallon. Okay, so number 4, which of the following correlation coefficients, so these are different R values, which one has the strongest association between the variables? Well, you look at the list here, it's tempting to say 0.78 because that is the largest number. But strongest just refers to the strength, and that could be positive or negative strength. So the strongest would be the one that's closest to either positive 1 or negative 1 if you have negative values. So I'm going to go with this negative 0.98. So we can say it has the strong association because it's the closest to negative 1. So don't forget, even if they're negative values, you want to think of it like a magnet. The negative 1 pulls it towards the negative 1. 1 would pull numbers towards that. So whichever one's closer to either positive or negative 1 distance-wise, that's going to have the strongest association. And then the last question, when doing a regression analysis on a data set, which of the following remain the same, no matter which variable is chosen for x and for y? Well, it's not the y-intercept and it's not the slope, because remember, those both give you the equation of the line. The equation of the line changes depending on which variable is x and which variable is y. What stays the same, though, remember, that was the correlation coefficient. So that will be the same regardless of which is your independent and which is your dependent variable.